Hi, welcome to the 10th lecture on topology. This is going to be the second lecture on closed sets. Okay, so let us get started. So as usual, references are the same. So let us quickly recall. In the last lecture we said A is a subset of a metric space, topological space when A is not closed. Okay, that means A complement not open. Okay, this is my X, this may be my A. If it's not closed, this is not open. That means there is a point X, okay, in A complement. So I have an okay, this I have to put as dot dot dot. This is, think of this as open thing. Okay, so this may be my point X. Okay, therefore if I take any small open set, okay, so that for every open set U containing X, U is not containing A complement. What does it mean? That means there is a Y in U, so that Y is not in A complement. That means there is a Y in U, so that Y belongs to A. What does that mean? That means there exists an X in A complement, so that for every open set U containing X, there is a Y in U intersection A. That is, U intersection A is not empty. Please go through this logic. So as I said, these points therefore are very important. This gives us an idea, the points X which exhibit this behavior. What kind of behavior it does exhibit? Whatever open set U containing X you give me, U will always intersect A. Such a point is missing in A, right? Because it is in A complement, that means it's not in A. Do you understand? Yeah, right. In other words, there exists a point X in X, so that for every open set U containing X, U intersection A is not empty, but X is not in A, because X belongs to A complement. You understand that? Yeah, because this kind of logical thinking is somewhat difficult, so I'll just go through it. If you need, again I will write a PRP. I hope you don't mind. So if you are very good, if you are very quick, I am very happy. Yeah, so this allows us to first, okay, let me use the standard convention. Okay, when I say U is an open set containing such that X belong to U, okay, this is always defined. Okay, this is same as saying U is an open neighborhood of X. I will write this NBD. Okay, because it's very, somehow it is easier to say it's an open neighborhood of X, okay, rather than use an open set such that X belong to U or U contains X. This is a very universal thing, all over the world one uses this, so let me also use that. So let us go back to the, therefore now I isolate this definition now. So such points are very important. They have something to do with A being closed or A being not closed, right? So let us do that. Let A be a subset of a topological space. Okay, then X in X is an adherent, okay, ADHERENT, adherent point. If you don't know that word, don't worry, I will explain that. Adherent point of A, if for every open neighborhood U of X we have U intersection A is not empty. Yeah, see, adhere means it sticks to. The same as saying stick to something. Okay, the word adhesive for paste also came from this adhere, adhere to. So if you want, you can call it sticky point. Okay, I usually okay, let's not worry about. Is that okay? I don't want to confuse you at present. Understand this. So what does it mean? So let us look at that. I have x and I have a, and x is an adherent point, meaning what? Whatever neighborhood I take, okay, that always intersect a. Okay, this may be the point, right? So what we want to claim, this is a lemma. What we observed is the following. I will again prove it. Let a be a subset of x, then a is closed if and only if every adherent point lies in a, right? So again, try to understand what is an adherent point. X is an adherent point. If you take any open neighborhood u of x, then u always intersect C, right? Is it okay? The proof we had already seen, but just to make sure that you understand, okay, we will go through it. So let a be closed, okay, and x in x an adherent point of a, right? So what do you have to prove? To prove x belong to a. Suppose not, we will prove by contradiction. What does it mean? If I take u equal to a complement, that means x belong to u, right? Suppose not, that means x is not in a, that means x is in a complement. What do I know about a complement? A is given to be closed, therefore what do I know about a? This is open, and therefore this is an open neighborhood of x, because x is there, right? Therefore it's an open neighborhood of x, right? Since it's an adherent point, since x is an adherent point, and of a, what do I know? U intersection a is not empty. Yeah, right, I wanted to say it is in x. If it's an adherent point of a, then U intersection a is not empty, right? But that's a nonsense. Why? Because u is, that is a complement intersection a is not empty. This is absurd. Okay, this is a contradiction, right? So this contradiction shows x belong to a. Okay, pause, review, proceed. Now let's prove converse. Okay, so if x is an adherent point of a, then x belong to a. This is hypothesis. So to prove a is closed, again we prove by contradiction. This is exactly what you have seen earlier. Okay, those of you who had already understood what I said in the first few minutes of today's lecture, or last few minutes of yesterday's lecture, last lecture, should stop here and try to prove on your own. Okay, for others I will just give proof. Suppose a is not closed. What does it mean? This means b equal to a complement is not open. That means what? It's not an open, that means there is an x in b, so that if u is an open neighborhood of x, yeah, u is not contained in b. Just let's try to understand, because logic is always somewhat you should go through my foundation course. Suppose when do you say B is open? B is open meaning for give me any x in B, okay, there is an open set, okay, right? U open neighborhood U of x such that U is contained in B. For example, I can take U equal to B itself. Do you understand that? Yeah. So if B is not open, that means what? There exists x in B such that for every given any open neighborhood U of x, U is not contained in B. This is what I proved. Yeah. Are you following? Again, that's just logic. This is what I used earlier, but I am just repeating because many students find topology difficult because the logical thinking is not properly trained. Okay, suppose I have an x in B, so that for every open neighborhood U of x, okay, even if there exists, okay, if there exists an open neighborhood U of x, so that okay, x belong to U is contained in B, then call it Ux if you want. Then B is going to be x in B of Ux. These are all open, therefore B is open. You understand? But our assumption is B is not open. Therefore, what does it mean? There exists one x in B, so that give me any open neighborhood U of x, then U is not contained in B. Do you understand that? Okay. If U is not contained in B, what does it mean? U is not contained in B. That means there exists a y in U, so that y is not in B. That means there is a y in U, so that y is in B complement, but B complement is A. You understand that? So what does it say? So for every open, so there exists an x in B, so that for every open neighborhood U of x, okay, U intersection A is not empty. This means x is an adherent point of A. By hypothesis, x must be in A, but where did I take my x? My x was in B, but by assumption x is in B, which is A complement. This is a contradiction. Yeah. So what have you proved? If every adherent point of A lies in A, then A is closed. Okay, please go through the proof. Those of you who have logical problem, please go through it at least twice. So let's stop and see what we had achieved. What you had achieved is the following. If suppose you give me a subset A of x, then I want to say A is closed. Okay, there are two ways of doing. First is by definition, that is only A complement is open. This is our definition. So if you want to prove A is closed, what should I show is A complement is open. Or I can prove the following. If x is an adherent point A, then x belongs to A. Believe me, this is the second thing is a very powerful characterization tool to show yes it is closed. And many of you would have learned the word limit point, which I would call a cluster point or accumulation point. Do not confuse that with that. Okay, this is somewhat weaker. Adherent point is a weaker notion than the so-called cluster point. I will come to that later. Please do not worry about. Okay, because many textbooks will show that A is closed if and only if okay every limit point, that is a cluster point, belongs to A. But okay, but this is much easier, you will see. So let's look at some examples of adherent points. So let's look at the simplest case first. Suppose X tau discrete space. Suppose A is a subset of X. Then we had already seen any subset of A is both closed and open. So what do I know? Therefore, the only adherent points of A are elements of A, because A is closed, and by the last lemma, any adherent point of a closed set must be an element of A. Yeah, right. Yeah, before going further, I should have mentioned this. Yeah, and sorry, I'll just take a digression. Notice that any X in A is an adherent point of A. That's very clear. Why? If you use an open neighborhood of X, then U intersection A, X belongs to this, therefore it's not empty, right? Notice that this is not the case of the limit point. What do you know as limit point? I am not yet defined. If you don't know that, ignore that word. That's the first observation. Second observation, if X is an adherent point of A and A is a subset of B, then what do you think you can conclude? U intersection A is non-empty, right? For every open neighborhood. What can you say about U intersection B? U intersection A is a subset of U intersection B, but U intersection is non-empty. Therefore, yes, did I hear the answer correct? Then X is an adherent point. This is a very trivial observation, but it's good to have that. Okay. Now my digression is over. Let me go back to example 1. Right. X discrete. Right. A is a subset of X. Right. Now start with any X in A complement, just to make sure that we understand. Then I want to say X is not a cluster point. Sorry, X is not an adherent point. Okay. We already know that, but I just want to see that. Then what does it mean? So that we get used to that. We have to say, if it's not an adherent point, what does it mean? If it is an adherent point, for every open neighborhood U of X, U intersection is non-empty. If it is false, mean there exists an open neighborhood U of X so that U intersection is empty, right? This is what we have to prove. That means we have to prove this, right? See, think. Okay, if you learn to think logically, it's easy. Many people have problem, that's why they find topology to be difficult. Okay, you understand? Now again, let me go back my trade secret. So what is the simplest open set, open neighborhood of X in a discrete space? Singleton X itself, right? Now what happens with singleton X intersection A? Since X is not in A, that is in X is in A complement, this is of course empty. So we have proved this is not an adherent point. Yeah. So what should be the next example? Indiscrete, right? Let A be non-empty set now, right? Okay. Now, what do you think? The only open set, open neighborhood that you have non-empty open set is X itself, right? Therefore, and take any X in X, right? Then what do I know? The only open neighborhood of X is X itself, and therefore X intersection A is non-empty. So what does it mean? Every X in X is an adherent point of A. Which A? A is just non-empty. That's all I need. You give me any non-empty subset A of X, in the indiscrete topology, every point is an adherent point of A. So now let's look at R with usual topology. Even with Rn I can do, but let's do that. So let us start with the set A. Let's say an open interval AB. Yeah, I want to know whether it's an adherent point. So this is my A, this is my B, right? Now start with any x, okay, which is strictly greater than x is strictly greater than B, right? Now do you see something interesting happening? So I can find a small thing, right? So this is, yeah, look at the distance between B and x, take the half the distance, then this interval is not going to intersect AB at all. Therefore this is, call it so U, then U intersection AB is empty. Therefore what I have shown, if x is greater than B, x is not an adherent point. Kind of A. And similarly for B, we accept it. Suppose I have y which is strictly less than A, then also y is not an adherent point of A, right? Okay, now every x in AB, this is an adherent point, we know that. So the only thing left out is what? X equal to A and x equal to B case, right? That's, I think, is very easy. So I have A, B, let us look at B. Choose any small open interval, okay, B minus epsilon to B plus epsilon, then there always exist points. That is right. What are the typical open sets? Remember, that's what you should look at, typical simpler open sets, okay, containing B. They are the open intervals. So I can as well cut down the length of the interval so that I can assume the B minus A is strictly greater than A. You understand? Choose epsilon positive so that B minus A is, see, I can choose this also as a B minus epsilon to B plus epsilon, right? So I am choosing epsilon so that B minus A epsilon lies in the interval. Now look at the midpoint of this, B minus epsilon plus B by 2, okay, this will be in this interval. Yeah, so this is greater than B minus epsilon and B is greater than this, right, which is greater than A. Therefore this point lies in the interval AB. Okay, these kind of things are never shown by picture, only usually shows, but you should learn how to write a rigorous proof. Okay, pause, review, proceeds. So what I will shown is, okay, the adherent points, okay, or any element of the closed interval AB is an adherent point of the interval AB. Okay, let us look at one more example. Suppose I start with Q set of rationals, right? I want to know what are the adherent points. Okay, so what do I do? Okay, start with any a real number. I want to know whether A is an adherent point and of Q. This is a question. So what I have to do? I have to find a typical open interval, open set containing A. So naturally I will get some for small epsilon, A minus epsilon to A plus epsilon. Now what do I want to know? I want to know whether this interval intersects Q. Do you know that or not? All of you know that, right? From real analysis, it's called density of rationals. Right? So given any two real numbers A and B, okay, there is a rational number, so that right, that's what is meant by density of rational. Now I have A minus B epsilon is less than A plus epsilon, therefore I know there is a rational number R. which belong to this. That means what do you think I have proved? Every real number x is an adherent point. In where? In R with usual topology. Yeah. So similarly, you can prove, or if you take set of irrationals also, by density of irrationals in R, you get the same result. Okay. Pause. Review. Okay. Now let's look at the fourth example. I hope this is the fourth example. Yeah. So let's look at the fourth example. So now let's look at R with let us say VIP topology. Of course, 0 is the VIP, right? Okay. Now let's look at my set A to be singleton 0, right? Now let A be a real number, or let X be a real number, right? I want to know that X is an adherent point. So, right? To check that, what should I do? I have to check any arbitrary open neighborhood of X should intersect 0, right? What's the simplest and smallest open set containing X? Assume X is not equal to 0 to start with. Okay, the simplest open set containing X is X comma 0, and if U is any open set that X belongs to this in the VIP topology, you will have X and 0 also, right? Now, therefore, what do we know? X intersection 0 intersection A is not empty because 0 is there. Do you follow? So every non-zero real number is an adherent point, but we remember any element of the set itself is an adherent point. Therefore, what do you think I have proved? Every X in R is an adherent point of the singleton 0. You see that? Just contrast this with the earlier case. In the usual topology, we wanted a big set Q, right? That was our A. Then we wanted to say every real number X is an adherent point of U in the usual topology, and similarly R minus Q. These are all very big sets. Whereas here, one single set is good enough. Everybody wants to stick to this set. That's of course obvious, right? If there is a VIP, everybody wants to clamor, right? Everybody wants to reach him. Yeah, that's what it says. That's why I called it a VIP topology, right? And suppose A is a set, okay, contain an R minus 0. What are the adherent points of this? Yeah. What are the open sets? So this is R minus 0, right? Are you following? I have this. This is my VIP. So he is thrown out. Now I have some A. What were the adherent points? You start with any open set. Okay, to start with any X. Suppose X is an R. Okay. Then what does it mean? X singleton 0 should contain R minus 0. This should be non-empty. Yeah. So what does it mean? 0 cannot be there. Therefore, X must be the only element. You follow that? Yeah. Are you following or not? But there is an easy way out. Let's look at R minus 0. Okay. A is a such R minus 0. Right. Then what is A complement? A complement is contains 0. 0 belongs to A complement. Therefore, A complement is open. Therefore, A must be closed. That means what are all the adherent points? Okay, the only adherent points of A are its elements. Yeah, so this is good enough. I don't want to keep doing all the such things. Let's take R with the outcast topology, okay, and investigate. This is an exercise for you. Okay, these are all very simple examples. So the best thing is go back and try to understand. Okay, now let's look at sixth. Suppose I have a metric space XD, right? Let's look at PXR, the open ball, right? Now let Y in X, or let us say A, let me call it A here, okay, BAR, open ball BAR. Let us start with an X in X, that the distance between A and X equal to R. That is, utility, what do I have? I have open ball this, okay, and my A is going to be exactly at the distance R. This is here, and this will be my, sorry, this is my, I'm sorry, this is X, and this is my A. Yeah, I want to know whether X is always an adherent point. This is the reason why I am saying adherent point of the open ball BAR. We want to know this. Because if you look at picture, the way we draw in the Euclidean space, it looks it's always true, but in general, okay, I want to say it's not true. Okay, because not always. Always. Why? Let's look at X D, where D is a discrete metric. Okay, and assume that X has at least 2 elements. Right? Now what happens? Start with A, fix an A in there. What is BA1? This has only singleton. And what is B closed ball BA1? That is all of X. You understand? Therefore, if I take an X in X, such that X is not equal to A, right? Do you see a problem? Because let us take the open set B, X1, that is singleton X, okay, then U intersection A is empty. Right? So what have we shown? So please understand. So what we have shown is, okay, if X is such that distance between A and X equal to R, it may happen that X is not an adherent point of the open ball BAR. Okay, this is something many people miss, so caution. Okay, this is a caution. Okay. But on the other hand, if I take X equal to Rn with my D to be one of the standard 3, D1, D2 or D max, okay, I am going to show, okay, the set of adherent points of any open ball BAR is the closed ball BAR. You understand this? Contrast this with the earlier case. And many times this is used in complex analysis and elsewhere, or even functional analysis, but you know, because of the picture, people believe it's true and then they go ahead, but it's not true in general metric space. Only here In any non-linear space also it's true, but you can ignore such words. Okay, how do I prove that? The proof is very interesting. It's very geometric also. Maybe I should, yeah. Okay, so this is, let me say, BAR. Okay, this is my A, right? Now start with an X, so that distance between A and X is R. Notice that this is same as the norm is equal to R, right? What are the norms? Okay, any one of the D1 the norm, this, okay, that's why you should watch. Okay, if you want, think of Rn with Euclidean metric, right? Norm of X is summation xi whole square to the power half, which is x dot x to the power half, etc. All these things you must all learn. Okay, right? But this is true with respect to any D1. That is what are the norms? The norm which is summation mod xi, and this is x2, which is xi squared to the power half, and this is a max norm, which is maximum mod xi. Okay, please, okay, watch my videos on metric spaces. All these things are explained there. I don't want to spend time on this. Okay, now the interesting thing is, remember, Rn is a vector space. It is not just a metric space, it also has a vector space, and the metric comes from a norm. That's what we are going to use. Therefore, I want to look at the line segment joining A and X. So how do I define the line segment? This is by notation. This is, I call it a line segment joining A and X. Okay, this is the subset. Okay, 1 minus t times A plus t times X, 0 less than equal to t less than equal to 1. This is called a line joining A and X. Okay, you know that any open ball in a, okay, with respect to Rn with any other norms, that is going to be convex. All these things you must have seen in your several variable calculus also. Okay, so do you understand this? Now what t equal to 0, what is this? This is A, and t equal to 1, this is X. Okay, are you following? So it starts at t equal to 0 at A, and t equal to 1 reaches X. Right, now it's easy to show that this point, let me call it zt equal to 1 minus t times A plus t times X, where 0 less than equal to t less than equal to 1. I want to say zt belong to BAR for every t. Okay, so how do I do that? I only have to do zt minus A. Now I want 0 for less than equal to 1, therefore then in that case, okay, let me say that yeah, for 0 less than t less than 1, even less than or equal is okay. Only equal to 1 I should avoid, because it will be at the end point. So what is this? This 1 minus t times A plus t times X minus A. Yeah, now do you see something interesting happening? Right, what do you get? 1 minus t times A, that is A minus A get cancelled, so therefore I am going to get mod t into X minus A or A minus X, yeah, whichever, A minus X minus A, right, minus TA plus Tx, that is t times X minus A, but that is mod t, which is t times norm of X minus A, that is t times norm of X minus A, that is less than R. Yeah, because X minus A is less than R, and t is also less than or equal to 1, therefore it's less than R. Right, so see X minus A, sorry, X minus A equal to R, sorry, because I am assuming X on the boundary. Okay, X is on the boundary, sorry, therefore it's less than or equal to r. But my t, I am saying 0 is less than or equal to t, strictly less than 1. Therefore, this is less than r. Therefore, what I have shown, for 0 less than or equal to t less than 1, zt lies in the interval bar, lies in the open ball. Do you understand that? Yeah. Okay. Now, and at t equal to 1, z1 equal to your x. Okay. Now start with any a and any x. Suppose I have an epsilon ball around this. Okay. What am I supposed to show? I want to show x is an adherent point. Now BAR. To show that, what do I have to do? I have to take any open neighborhood of x and show it has to intersect BR. But any neighborhood of x will contain an open ball, right? Therefore, U is an open neighborhood of x. Then there exists epsilon positive, so that Bx epsilon is contained in U. Therefore, it's enough if I show Bx epsilon intersection BAR is not empty, as the picture shows. Yeah, but that's very easy. Yeah, because I am going to claim if t is very near to 1, then zt will be in Bx epsilon. But we had already seen zt's are where? In BAR. Therefore, what do you think I have shown? I have shown that, okay, all these fellows are going to be there. That's what the picture shows, but I have to prove that. That's very easy, right? How do I do that? That means zt minus x, this norm, I have to make sure is less than epsilon for t near 1. But what is this? This is 1 minus t times a plus t times x minus x, right? But that is 1 minus t times a, and here also, you see that? Yeah, minus 1 minus t times x, or plus 1 minus t times, I'm just to make sure that I'm writing correctly. Yeah, minus this x, therefore minus x. Yeah, but that is equal to 1 minus t times norm of x minus a, right? But that is less than 1 minus t times r. This 1 equal to 1 minus t times r, because norm of x minus a equal to r, right? So what do I want? I want this to be less than epsilon. So what does it mean? If t is very near, okay, that means, yeah, 1 minus t should be less than epsilon by r. Yeah, so you know how to make t. So 1 minus, if t is very near to 1, it will be less than any positive number. You follow that? Therefore, what do you think I have proved? Please, this example is usually never done in any topology book, except perhaps in my functional analysis and complex analysis book and forthcoming topology book. So please learn that well. So in Rn, okay, with d1, d2 or d infinity, or more generally in any nonlinear space, okay, BAR, okay, adherent points is BAR, the set of adherent points of the open ball is the closed ball. This is something fantastic geometric. Okay, please pause, review, proceed. Okay, in the next lecture we will also put this thing to use. There will be 1 or 2 more examples I may want to do, but I think I have given a lot of examples about adherent points. Please go through that, learn how to work with them. Okay, so, and believe me, most of you, if you have learned topology, you will be, your teachers, books, everybody is obsessed with the word limit point. Okay, and you will be surprised, in ordinary topology, almost, in fact I would say always, you need only adherent points. Okay, then where do you need the so-called limit points, which I call cluster point? Only when you want to define the limit of a function, and especially if you want to show the limit is unique with the domain codomains of Hausdorff space. And second place is in the so-called Orson-Weierstrass property of compact spaces. Any infinite subset of a compact space has a limit point. But believe me, this second part I have never used in my life. First part, of course, any analyst has to use it. Apart from that, I don't see the role of the so-called limit point, which I call cluster point, in general topology. This is a very politically damaging statement, but I am making it. Okay, please go through it, learn the point well. We'll meet again. Take care, stay safe.